Welcome to day 3 of graphing rational functions. Today's primary topic is removable discontinuities. So go ahead and write this definition in your notes and take a moment to think about what it means. You can pause the video while you take a moment to do that. So to understand what a discontinuity is, we first need to understand what it means for a function to be continuous. A function is continuous when there are no breaks in that function. So if we're drawing the function and we don't need to lift our pen, this function is continuous. You have seen one type of discontinuity previously, and that's where we have a vertical asymptote. When you're drawing your function here, the function cannot cross the asymptote, so you have to lift your pen to continue on the other side. A removable discontinuity is just a hole in your graph. So if we're drawing our function, we'll place a hole where that discontinuity exists and then continue drawing the function. Our discontinuities exist where the denominator is equal to 0 because they exist where the denominator is undefined. So the difference between these two is that a removable discontinuity exists when the same factor exists in both the numerator and the denominator of the function. Let's go ahead and take a look at the first example here so you can see what that looks like. We will start by factoring. So the numerator is x minus 4 times x plus 1, and that is divided by x minus 4. We have a common factor of x minus 4, so we'll divide out that term. And our simplified function is just y equals x plus 1. When you graph these functions, you will be graphing the simplified version. So let's go ahead and identify our hole and then graph the function. So our hole exists when the function is undefined. So where x minus 4 equals 0. So our hole is at x equals 4. And the hole occurs at a particular point on the graph. So we need to figure out what the value of y is when x equals 4. And we'll use our simplified function to do this. So when x equals 4, y equals 4 plus 1, which means y equals 5. So our hole is at 4, 5. Let's go ahead and graph that. Over 4 and up 5, we'll place our hole. And this function is just a linear function, so we don't need radii to graph this function. We can see our y-intercept is at 1. When x equals 0, y equals 1. And you can graph more points if you would like, but we can see with just these 2 points how to plot this because it is linear. So that's what your function looks like. Number 2, again we'll start by factoring. So we have a GCF of 5 in the numerator. 5 times x minus 3 divided by x minus 3. Common quantities x minus 3 can be divided out. So our simplified function is y equals 5. Again, we don't need to use radii, so let's identify our hole. The hole occurs where the original function is undefined, so where x minus 3 equals 0. So we have a hole at x equals 3. And this needs to be a point where the hole occurs. So when x equals 3, what is y? Y is always 5. So when x equals 3, y is 5. The hole occurs at 3, 5. So we'll go over 3 and up 5, place that hole. And to graph this function, y equals 5, it's just a horizontal line. So there's our graph for number 2. Alright, number 3. On this one we have a common factor of x in the numerator and the denominator. So we can use our properties of exponents to reduce this to x squared. So our simplified function is y equals x squared. Our whole occurs where the original function is undefined, so where the denominator x equals 0. And our y value at this point is going to be y equals 0 squared, or just y equals 0. So our whole occurs at 0, 0. Let's go ahead and plot that whole first. And the simplified function is just the parent of our quadratic functions. So let's plot a few points for this parabola. These are just our squared terms. 1, 1, 2, 4, 3, 9, and also on the negative side, negative 2, 4, negative 3, 9. So our function looks like this. On these linear and quadratic functions, you need to be more precise than what we were doing on day 2 of rational functions, because on these ones you can easily find your points and plot your graphs. So if you want full credit, make sure that you are going through those critical points. So for number 4, we'll go ahead and start by factoring our denominator of x plus 2 divided by x plus 2 times x minus 1. Here we have our common factor of x plus 2, so we'll divide out that term, and our simplified function is 1 divided by x minus 1. You'll notice that this is just a transformation of our parent function, y equals 1 over x, so we can use transformations to graph this, or we can use our radii values. I will do both just so you can see how both methods would work. First, let's identify our whole. The whole occurs where we have that common numerator and common denominator, and where the denominator is equal to 0. So x plus 2 equals 0. We have a whole where x equals negative 2. So our y value when x equals negative 2 is 1 divided by negative 2 minus 1, which is negative 1/3. So our whole will occur at negative 2, negative 1/3. Let's go ahead and draw that now. Negative 2, negative 1/3, right there. So plotting this function, y equals 1 over x minus 1, using transformations first, we need to identify that a equals 1, right, that top number. Our h equals 1, which is this here, x minus 1, so h equals 1, and our k equals 0. So the only transformation is that we are moving right 1. So let's put a point there, moving right 1 from the origin. And remember that that point is the intersection point of our vertical and horizontal asymptotes. So now we can plot our parent function by putting down a few points, our negative 1 from that intersection point, and our 1, 1. We'll have another point at 1/2, 2, 2, 1/2, and again on this bottom left side, negative 2 down 1/2, negative 1/2, negative 2. And again, I'm saying these values based on the intersection point of our horizontal and vertical asymptotes. So then we can connect those points like so. We don't want to go through that hole. We want to leave that hole open. Alright, so that was a pretty bad drawing. You can do better. If we want to use radii, our roots are where the numerator equals 0. So 1 equals 0. Well, that can't be possible. So 1 does not equal 0. There are no roots. And we can see that because there is a horizontal asymptote at y equals 0. So our vertical asymptote occurs where the denominator equals 0, x minus 1 equals 0, so at x equals 1. There are no multiplicities of 2 in the numerator or denominator, so we have no tangency, and the graph does not come together. Our end behavior is at our horizontal asymptote, and here we can see that it is bigger on bottom. Our degree is 1, and on top our highest degree is 0. There is no variable in the numerator, so y equals 0 is our horizontal asymptote, and our y-intercept occurs where x equals 0. So at y equals -1, and the point at y equals -1 is going to be 0, -1. So right here we can see that y-intercept. So that's just a review of what we saw in day 2, but again, this one is just a transformation of the parent function, so you can use either method. So number 5, we're going to factor our denominator. We have x plus 1 divided by 3x. I have a 2 here, x and a 1. So here we need a positive x, so we'll have plus here and minus here. So our 3x minus 2x gives us that positive x, our 3x times our x gives us the 3x squared, and our -2 and our positive 1 give us that -2. So the common factor here is going to be x plus 1. And our simplified function becomes y equals 1 divided by 3x minus 2. Let's identify our whole. So where x plus 1 equals 0, we have a whole where x equals -1. When x equals -1, y equals 1 divided by 3 times -1 minus 2. -3 minus 2 equals 1 over -5. So our whole occurs at -1, -1 over 5. -1, -1 over 5 will be right there. And let's go ahead and use radii to graph this. Again, this one's just a transformation of our parent function. But let's use radii. 1 is not equal to 0. So there are no roots. Our vertical asymptote occurs where the denominator equals 0. So 3x minus 2. We will have x equals 2/3. So right about here. We do not have any multiplicities of 2 in the numerator or denominator. So no tangency, and our graph does not come together. Our end behavior, our horizontal asymptote, again, comparing our highest degrees. In the denominator we have 1, and in the numerator 0, x to the 0. So it's bigger on bottom, which means our horizontal asymptote is y equals 0. That'll be right there. And our y-intercept. This occurs where x equals 0. So where y equals negative 1/2. So 0, negative 1/2 will be our y-intercept. So right about there. So we can go ahead and graph this using our 2 points on the left. And then on the right side, we know that the graph does not come together, so it cannot be in this bottom right corner, which means it must be in this top right corner. So that's the graph for number 5. Number 6. I'm going to get you started here, but then I want you to work on this one on your own. We'll start by factoring our numerator and denominator. We'll have x minus 2 to x plus 1, and then in the denominator x minus 3 and x plus 2. Now the one thing to notice here is that we do not have any common factors in the numerator or the denominator. So what does this mean about our wholes? There are none. So you will be using Rady to graph this function. You can go ahead and graph it, and I will check it tomorrow when I check the notes. You must have this completed to get full credit for your notes.